Hello everyone and welcome to the YouTube channel for Wayne State University's chapter of the Tau Beta Pi Engineering Honors Society. My name is Austin Heitzman. I am back again with another installment in our Linear Algebra mini-series, if you will. We've officially made it past chapter 1. Congratulations on making it this far. I hope your exams went well, if that's applicable. Today we're going to be starting off with chapter 2. And this chapter is kind of tiny but mighty. There's only 3 sections in it, but it covers basically like linear combinations and like independence versus dependence. Very important concept in the whole course, pretty much. So highly recommend that you try to buckle down and really get this under your belt, and we're going to have fun by doing it together. So before we can get into any of the true bulk of the chapter, we need to start by talking about something called vectors in R superscript n. And to do that, we're going to start by talking about something called Euclidean Space. And after Euclid, you've no doubt heard about him for any geometry class. So to start with the familiar and ground ourselves in something we know, 2 space is going to be denoted by this kind of R to the superscript 2, right? And maybe you've seen this R before as like referring to like all real numbers, right? So R to the superscript of something is going to be kind of the same idea, but like all real like coordinate pairs with 2 points in this example, right? And we can see this in terms of something we know. If we denote this in set theory, then it's going to look like a vector x1 and x2, just to keep this super gentle, or general I should say, excuse me, such that x1 and x2 are are all real numbers, right? In that set of real numbers. So this is pretty much going to be any vector with 2 components, we could say, right? Similarly, Euclidean 3 space is going to be denoted as R superscript 3. I'm sure you can see where I'm already going with this, but just the same way, we can write this in set theory general notation to basically denote that this is any vector with 3 components, and each component is a real number. And we can generalize this even further by going to n space, right, which is going to be R superscript n. And this is basically the same thing, but like n is not really restricted to being 2 or 3, you know. We can see this further by writing the set theory notation as follows. If you remember us from chapter 1, we have all these like really general notations with the dots and everything denoted that there's a lot of things in between up until x n. And we're going to write this in set theory notation as xi in the set of real numbers for I equals 1 to so on and so forth all the way up to n, right? So like it seems a little silly even going through this. It seems kind of apparent, but this is important to lay out so that we really know like what we're dealing with, right? And I've mentioned that like we can kind of view this as like a vector with n components, right, for n space. But it is good to like really lay that out. So geometrically, if we're just looking in R2 and R3, right, we can say that a vector, this word that we've been throwing around this whole time, is a directed line segment from the origin to a point whose coordinates are equal to the components of the vector. Let's break this down for a second. So directed line segment, we've already mentioned that vectors are magnitude and direction. In other words, they're an arrow, right? They're pointing somewhere. And where are they pointing? Well, they're going to start at the origin, 0, 0. If we're in R3, it would be 3 zeros. And it's going to extend to some point, x, y, z, right? And the coordinates of that vector, so basically like when we say like a vector having coordinate x, y, z, that's going to be equal to the components. And the components, very simply enough, are just the vector entries. So in this case, if this is a vector, then x, y, and z are components. If we go up here, the x1, x2, so on and so forth to xn, those are all vector components. So yeah, basically just like what makes up the vector. And as I was writing this out, I was kind of considering like, why are we restricting ourselves to R2 and R3? Basically, like anything beyond R3 gets complicated, if not impossible, to graph. And this definition is really relating to like what the geometric implications are. So that's not to say that like a vector in R superscript n is not a vector. It's just that we can't really like represent that in the same way that we can for 2 space and 3 space. So maybe this at least will like ground you in something visual. And to do that, I'm just going to do like a really quick graphical sketch, just like a little example, right? So if we have, we'll do this in 2D because I think I mentioned before, like my 3D graphs are just like abominable. Let's say that we want to graph a vector with points 1 and 2, right? Well, this is going to be very similar to just graphing a point, right, at 1, 2. But instead of just having that point sit out in the middle, go from the origin, right? Because we're going from the origin to the point. And now we've drawn a line segment. But in order to make this a vector, it needs to have direction, right? So you can just put an arrow at the top. And that is going to be the vector in 2 space with the coordinate and the components 1, 2, right? So again, hopefully this like gives you something visual to work off of, but in this class in general, since we're getting into higher level dimensions or n space instead of just 2 or 3, it's more general to use like the algebraic definition, but I always think it's helpful to just like have something in your mind to actually connect it to. And there's a couple small points to note about this. So basically we can say that a vector is unchanged if it is relocated on the plane with no change in magnitude or direction. What does this mean? It basically means that if we have this graph again, let's extend it out this time. Well, if I have, we said we had like 1, 2, right, as our original vector, right? Well, if we instead take this and instead of the origin, it's positioned at, say, 3, 2, right? Well, as long as it still goes to the right one and up 2, that's going to be the same vector. All right, and that's going to be really useful if you ever encounter something that's not centered at the origin. And it just reminds you that you can move it right to the origin. It's going to be a lot easier to work with. Similarly, the origin is so convenient that it even has a special name. Vector is in standard position if its initial point is the origin. All right, so now that we have like an idea of Euclidean space as it relates to vectors, let's look at just some general properties of vectors. And this is really going to ring a bell if you remember looking at like properties of matrices. Very, very similar. So let's look at vectors in detail. So if we have u and v, and these are both vectors in n space, right? And similarly, we have a scalar, we're going to call it c, then the sum of u and v is just going to be the sum of components, right? And what does that look like? Let's say u plus v equals this vector u plus this vector v and that just equals u1 plus v1, u2 plus v2, so on and so forth until you get to un plus vn. Very simple. Did the same thing with matrices. This is nothing new. And similarly, the scalar product for a vector is just going to be the scalar multiplied by each component. So if we have scalar times v, we'll say, it's going to be the same thing as putting that scalar on the outside of v. And that is going to equal scalar times the first component, scalar times the second component, all the way down. And what do we notice about these vectors? Have the same properties as matrices. This is going to go for like the distributive property, associative, everything, so on and so forth. It does make this pretty straightforward. You know, we're not really doing too much new yet. We're just kind of repositioning our reference frame, if you will. There's a couple additional notes that I wanted to cover here. We have something called the zero vector, which seems trivial, but is honestly pretty important when we start getting to combinations and independence. And the zero vector is just a vector with n components, all of which are 0. So in practice, this basically just looks like 0, 0, all the way down to 0. All zeros in between. We also have that additive inverse, which basically just takes the negative of each component. So for example, if we have vector v equaling v1, v2 down to vn, be additive inverse of v is just negative v1, negative v2, all the way down to negative vn. And this is pretty much going to be like subtraction, right? I mean, you can essentially think of this as that scalar multiple we talked about if that scalar is -1. So again, really nothing new. The only little difference is that if you'll remember from matrix multiplication, we need that special stipulation, right? We need to have the number of the first matrix's columns equal the number of the second matrix's rows, right? While for vectors, you can have as many rows as you want, but it's only going to ever have one column, so that does not work. So technically, you cannot multiply vectors. Can, however, use like dot products or cross products. Instead. And that's pretty much going to get back to like when we did use multiplication on vectors, we were essentially like taking the dot product, right, of just like each row and column respectively. So if you need a little refresher on that, you can find that in some chapter 1's videos. But as it is, it's not really something that we need to look at too in depth. And honestly, this is pretty much the bulk of what this first section talks about. It does seem a little bit simpler on the surface. So we're just going to dive right into an example, and it's going to be a pretty simple example. I do want to point out, though, that something I realized actually as I was putting this thing together, if you are using the same textbook that I am for this class, which is mentioned in the description of this video, what I did not notice until after we already started like getting through the rest of this chapter is that for some reason, and I don't know why, most of the exercises for this section deal with things that they don't bring up until the next section, right? So like half of the exercises are going to deal with things like, like converting like the vector into like its basic elements, or, like making it a combination of another vector. And I gotta say that like really stressed me out when I first saw that, because I felt like I was like really behind and like not understanding, but instead it was actually just like, we haven't covered that yet. So hang in there. We will be doing the next video on section 2.2, so after that it should make a lot more sense. But for now, we're just going to do an example like covering what we talked about here, right? So in this example, we have three different factors. We have u with the components 1, -2, and 3. We have v with the components -2, 4, 0. We have w with the components 2, 1, and -1. And we are asked to put this all together to find 2u minus 3 parentheses v minus 2w, right? Now, this is going to be honestly pretty simple. I mean, we've done these things with matrices before. We're just converting it to vectors, and like we just said, they have the same properties. So we know how to do this, right? The most important thing to note is just order operations. So we're going to want to like deal with the parentheses first, right? Sometimes it's easier to like write out all of those scalar multiples as you have them. But as long as you can keep those things in mind, you're golden. One thing I do want to note for this example is that the distributive property holds. So if you wanted to tackle this by distributing, you could say a -3 into this, so that this expression would essentially be 2u minus 3v plus 6w. That is fine. I think what I'm going to do here is just take this as it is and just start with what is inside the parentheses. Right? And I do tend to like tackling this just by writing out the scalar multiples first, and I will include any subtraction as just a negative to that, right? So if I'm going to start out with like a negative 2w, well, we have w being 2, 1, negative 1. So negative 2w is going to be negative 2 times 2, which is negative 4. And we have negative 2 and positive 2. Right? And then if we add that to v, right, v is negative 2, 4, 0. You'll notice since I took that subtraction sign as a negative into this negative 2w, we're going to add these. It's that additive inverse coming in. So the contents of the parentheses are going to be negative 6, 4 plus negative 2 is 2, and 0 plus 2 is 2. Right? So this right here is equal to this section, right? Now, if we want to next do the scalar multiples, right? So we're going to have a 2u, and we're also going to have a negative 3 this, right? We don't really have a name for that vector. Because of that, I'm going to do that first, right? So negative 3 times negative 6, 2, and 2. We're just going to multiply each component by negative 3. That's going to give us a positive 18, a negative 6, and a negative 6. And then 2u, well, u equals 1, negative 2, 3. So multiplying each component by 2, we have 2, negative 4, 6. So now, looking back, we have already included this subtraction sign as the negative in front of the 3, right? So we can just add these two together. Right, we do so by, again, adding each component. So this final answer is going to come out to 20, negative 10, and 0. And that's it. Hopefully this feels really familiar after all of the painstaking work we have done with matrices. And again, I know this section seems a little rudimentary, but it's going to be very helpful when we start digging into combinations and dependence. So stay tuned. I will have probably all of these videos posted together, but if you need help with either what's to come or what has already been covered, you can find those on our channel as well. Be sure to subscribe in order to get notifications for when we inevitably do a lot more of these as time goes on. Our channel also hosts a lot of other STEM-based classes, things like other math classes or chemistry, engineering, anything you can think of. So be sure to check us out for those as well. And in the meantime, best of luck getting this under your fingers, and I will see you next time. Bye.